Okay, chapter 7, lesson 6, talks about slope and similar triangles. So this is just another way to use similar triangles by talking about the slope. So they talk about slope triangles, which is basically if you have a line, such as this one right here, if you take almost like, you know how we count the rise over run, that type thing, rise over run, it does make a triangle. There will be a right angle in the corner of both. So that is one angle that they have in common. And actually, since you know that they have the same slope, those angles right there are congruent, as is those angles right there. So actually, all three angles are congruent. They are similar. They are similar. So you can use the properties of similar triangles to show that the ratios, the rise to run for each triangle, are equal. So rise over run, rise over run. So if you talk about this, this is 1, 2, 3, 4, 5, 6. 6 over 1, 2, 3. Divide that and you get 2. What is this? 1, 2, 3, 4 over 1, 2, which is 2. So those are similar because even the ratios of the sides are the same. So those are similar values. So example 1 right here. It says write a proportion comparing the rise to the run for each of the similar slope triangles shown above. Then find the numeric value. So we actually just did that. So let me go down here a little bit. So if you talk about AC, which was that line right there, AC is to BE as BC is to DE. Let me go back up just a little bit so you can see A. So AC is to BE as BC is to DE. That's what we talk about there. All right, so what are those values? 6 is to 3 as 4 is to 2. 6 is to 3 as 4 is to 2. So whenever you do that, you divide them out and you get 2. All right, that would be the length of that side right there. That would be the length. Okay, so 2 is actually the length of DE, which we had talked about. The height would, the height is 4. Get off of there. So when you make a proportion, remember cross products are even. Cross products are equal. So whenever we do the cross products right here, 6 times 2 is 12, 3 times 4 is 12. If I had those right there, notice that they both end up being the same amount anyway. So those are equal. That is our numeric value. So whenever it says it wants the numeric value, it's talking about this right here. It wants the actual proportion. So don't work it out to 2. I was just showing you how those work. Okay, moving on. Let's try one of your own. So let's do this one together since we have to graph. How about that? So it says the vertice M is 1, 2, 3, 1. N is 1, 0. And O is 3, 0. It's a little bitty guy. Oh, isn't he cute? Vertice, let's go ahead and put our letters on here, by the way. That's M, N, O. All right. And the next one, P is 5, 1, 2, 3, 4, 5, 2. Q, negative 1, negative 1. And R, 5, negative 1. So I've got that triangle right there. Then write a proportion comparing the rise to the run for each of the similar slope triangles. Find the numeric value. So when we write a proportion, we are going to say MO is to PR as NO is to QR. Now, what are the numeric values that go with that? So this rises 1, so MO is 1. 1 is to 3 as NO. 1, 2. 2 is to 1, 2, 3, 4, 5, 6. And doesn't 2, 6 reduce to 1/3 anyway? There are your cross products. 2 times 3, 1 times 6, they're both 6. That is our proportion. That is its numeric value. So not too bad. All right, let's move on. The ratio of the rise to the run of two sloped triangles formed by a line is equal to the slope of the line. So we knew that anyway. We knew that the slope of a line is rise over run. Okay? So this is just saying that you have two triangles. Right here they have this triangle here along with the line, and then they have this triangle down here. So they've got two triangles there, rise over run. So why would the slope up here be any different than the slope down here? The slope is constant all the way up and down that line right there. So surely it only makes sense that whatever the slope is here, the slope will be the same down there. So if you look at the larger triangle, it will rise 6 units, 1, 2, 3, 4, 5, 6, and run 1, 2, 3. 6 over 3. Now, notice they have a negative 3. Doesn't really matter if it's a negative 3 or a negative 6, but one of them has to be negative. Why? Because the line slants down. Remember, we said any line that slants down would have a negative slope anyway. So that's why it's negative 2. Smaller one. It will rise 1, 2, and run 1, and again, has to be negative because the line is slanting down. So it's still negative 2, either way. All right, so that's something that we kind of already knew, but maybe it puts a different perspective on it, give you a little deeper understanding of what we're talking about. All right, example 2. The pitch of a roof refers to the slope of the roof line. Choose 2 points on the roof and find the pitch of the roof shown. Then verify the pitch is the same by choosing a different set of points. So basically what they're asking you to do is find the slope of this line and then check it. Find the slope of the line and check it. This is the same slope formula you have been dealing with since what? Chapter 3? y2 minus y1 over x2 minus x1. So you would find the coordinates of the points, subtract them, get your slope. So the only other thing that they are talking about there, they're asking you to use, this point and this point. Maybe give me a different color there. Use this point and this point, or maybe use this point and this point. It doesn't matter. It's the same line. The slope will be there. Really doesn't matter. This is a rise 2, run, 1, 2, 3, 4. So the slope would be run half. Right here, rise 1, run 2, slope would be 1/2. So they're just asking you basically do it and check it. So whenever they say do it and then verify it with another point, they're just asking you to check it. Okay. Easy stuff, right? This is all stuff that we have learned before. They're just putting a different spin on it. But other than that, it's the same. Last one. The plans for a teeter-totter are shown at the right. Using points G and L, find the slope of the teeter-totter, then verify that the slope is the same at a different location by choosing a different set of points. So again, you can use slope formula, just like what we just talked about, or really it's already plotted on a graph. Why would you not just count them? So from points G and L, let's use that one. Talking about that triangle right there. How much does that rise? 2. How much does that run? 1, 2, 3. It's kind of hard to tell on my grid because I don't see a whole lot of lines. 1, 2, 3, 4, 5, 6. Let's even do this one right here. What about if we did H to G? What about that one? How many does it rise? 1. How many did it run? 3. Doesn't 2, 6 reduce to 1/3? What if I use this big one right here? What if I go K to G? How many does it rise? 1, 2, 3. how many does it run? Well, if that's 6, 7, 8, 9. Aren't these all equivalent fractions? 3/9 reduces to 1/3, 2/6 reduces to 1/3. That's what it is. So basically the slope of the line is the slope of the line. I don't care if you're talking about this part, or this part. All talks about you can make similar triangles. No matter which triangle you pick, the slope's going to be the same all the way up and down that. Really only makes sense. So with that being said, I really don't think you're going to have a problem with this lesson at all. But if you do, come see me. Good luck.